So if we go back to last week we spent a lot of time talking about gases in the gas phase. We looked into evaluations of temperature, pressure, energy. We talked about the gas laws themselves on Friday. Now, when it comes to transporting gases, there are a couple of options. We can compress them by just simply packing more of them into a container, getting a higher pressure as a result. And that's how most gas cylinders are. Again, if you think of normal pressure at 14.7 psi, a commercial gas cylinder can be anywhere between 3,000 and 3,500 psi. And a canister that you might buy for, a little helium tank or something like that might be on the order of maybe 200-300 psi. Now, compression is probably, again, the most common way that we can transport materials, because gases, as you know, have lots of space in between the particles. And so all that compression really does is it forces those molecules to get closer together. And by getting closer together, eventually they'll just start kind of knocking into each other a little bit more. And that's going to increase the pressure. But the other way that we can go about looking at these is by actually condensing them. Condensing the gases or the vapors, turning them into liquids, is an even more economical way of transporting them. Because with a gas, you have to worry about high pressure, you have to worry about what happens if this thing ruptures. With liquefaction, it's a liquid. You can store liquids within reason and transport them a heck of a lot easier than you could gases. Think about how you buy propane. Now, propane, if we had it at normal pressure, is a gas. But when you go to any one of the retailers here in town to buy propane, they're going to sell it to you in the liquefied form. Why? Because it's not terribly difficult to condense. It's a heck of a lot easier to sell it to you by the gallon as opposed to by 100 psi or whatever. Now, how do we liquefy these gases for transport, for commercial selling? Well, what we use is something called a phase diagram. And a phase diagram, we brought this to light on Friday at the very, very end. A phase diagram is essentially a graph. On the one axis, we have pressure. On the other axis, we have temperature. And based upon the values, we can predict when something's going to be a solid, a liquid, or a gas. Now, before we get into looking at phase diagrams more closely, there are some terms that are associated with phase diagrams that we need to make ourselves aware of. For example, the boiling point. Now, we know what boiling is. Boiling is that temperature where we get the liquid to turn into a gas. But more specifically, we need to separate what constitutes boiling versus what constitutes evaporation. I know that if I leave a glass of water out on the table, that the water inside the glass will evaporate away over time. Now, no one in this room would say that the water inside of that glass boiled out. We would call it evaporation. What's the difference, though? Both are liquids turning into gases. The primary difference between them is something called vapor pressure. When a gas evaporates, the vapor that comes off of that liquid exhibits a pressure. Now, at low temperatures, the vapor pressure is relatively low. As the temperature increases, though, think back to our Gay-Lussac's law, as that pressure and temperature increase, we're going to see both changing at the same time. So right now we've got water here at 20 degrees Celsius. If I turn that to 40 degrees Celsius, the amount of vapor pressure that was there at 20 is going to be higher at 40. And it's going to be higher even still at 60. And it's going to be higher even still at 80 degrees Celsius. Until we hit the point where the vapor pressure coming off of the liquid matches the vapor pressure of the atmosphere around it. And that, by definition, is boiling. When the pressure of the evaporated liquid matches the pressure pushing down on it, we say that that liquid is boiling. Normal value for water, 100 degrees Celsius. At 100 degrees Celsius, the vapor pressure of water turns into 1 atmosphere of pressure. But it is this exact phenomenon that explains why at higher altitudes, we have lower boiling points. Go up into the mountains where the air is thinner and the pressure in the atmosphere is lower, water boils at a lower temperature. Why does it boil at the lower temperature? The atmospheric pressure is lower, so we don't need to heat the water up as much to get the vapor pressure up to meet it. Now that wreaks havoc on all sorts of things related to cooking, baking, heating, anything really, because all of the things that we're used to being associated with at sea level are happening at considerably lower temperatures in higher it depends on the elevation. It depends on the elevation. Like Mount Everest, I want to say that the boiling point is in the 80s, up that high. For some place that's a little less extreme, like say Denver, Colorado, anywhere in the Rocky Mountains, you're talking about 95, 96 degrees, somewhere in there. So not insignificant. And certainly if you're doing things like you're doing any kind of high temperature stuff where you're looking for water to boil out of something and cook what's around it, that's why high altitude directions usually exist. Or what is prominent in a lot of those areas is using pressure cooking, where you don't have to worry so much about that because the pressure inside of the vessel is already elevated, so the water's going to get hotter anyway. Because a pressure cooker basically works on the opposite premise. Increase the atmospheric pressure inside of the vessel, and it takes longer for the water to boil, so it boils at a hotter temperature. And that in turn cooks the food faster because instead of hitting 212 degrees and basically stopping the heating process until all that water's gone, it can heat up to 300, 350, or whatever the case may depend upon the pressure inside. So that's the boiling point. And so we will usually think of things in terms of what we call a normal boiling point. The normal boiling point would measure the boiling point at 1 atmosphere. But understand that when pressure conditions change, our boiling temperatures will change as well. The triple point. The triple point is the point in the graph where temperature and pressure are given And what we have in that condition is all three phases all present at the same time. So for example, the triple point of water, which happens at a relatively low pressure, just slightly above the normal freezing point of water. At that condition, you find water in the liquid phase, ice, and steam all together at the same time. And what's even crazier about that is that they're all interconverting between each other at that point. So you see boiling, freezing, and condensing all at the same time, all at the same temperature and pressure. It's a pretty interesting phenomenon. Critical point. Critical point, this is the maximum temperature and pressure condition where a gas and a liquid are still distinguishable from one another. Meaning I can see, here's my liquid phase, here's my gas phase. At temperatures and pressures beyond this point, the two are indistinguishable. Can't tell them apart. And we actually take on a new kind of phase of matter of sorts. It's called a supercritical fluid. Now, depending upon the substance and what kind of forces hold that substance together, supercriticality is something that could be relatively easy to acquire or incredibly difficult to acquire. All depends on kind of what is holding the molecules together. Probably the most common example of a supercritical fluid, carbon dioxide. Carbon dioxide, as you know, is a gas at room temperature. Provided with enough pressure, we can compress it actually all the way into these little carbon dioxide pucks or nuggets or pellets or whatever. We call that dry ice. And what's kind of cool about them is, yes, we can cool the carbon dioxide down to do it, but technically all we really need to do is increase the pressure usually. But because of its dynamics, the critical point for carbon dioxide is actually relatively reachable. And it's useful in that regard because what you have in the supercritical fluid is a substance that has liquid and gas properties associated with it, which give it some kind of unique uses. Does anyone here get any dry cleaning done of any kind? Okay, Lear? Where do you get dry clean? Okay, why do you take them to a dry cleaner? Why not just throw them in the washer? Yeah, there are certain things, certain materials that your washing machine will basically beat the crap out of. And you don't want a nice $200 suit getting torn to bits by the agitator in your washing machine. So you take it to a dry cleaner. Dry cleaner works by basically knowing, okay, most of the stuff that you wear that you take to a dry cleaner is stuff that you kind of wear on top of other things. You know, you wear a suit, you're not going to go play basketball in the suit. You could. Most of the time, you're not. So what they do is they use a series of organic solvents to clean the stuff out of the suit. And because they're organic substances, they're volatile. And so once they do the job of getting the stains out or getting whatever out, for the most part, they either go down the drain or they evaporate. That's the dry part of dry cleaning. Now, the nasty part about that is that those volatile organic compounds, well, most volatile things are flammable as well. And so many a dry cleaner goes up in flames from time to time because the stuff that they use to clean the clothes is also incredibly flammable. Happened to me once. There's a dry cleaner a couple blocks from my house. An arsonist got a hold of it and just like that, I lost about 3/4 of the clothes I own for work. Luckily, they were insured. Luckily, I got most of that stuff back, but it took a while. The difference, supercritical carbon dioxide, because it is nonpolar, just like an organic, because it is a fluid that once we release it from its pressure and temperature conditions, it just evaporates like a volatile organic substance. Supercritical carbon dioxide can be used for some of the same purposes that we see for dry cleaning. The only difference, carbon dioxide is a completely 100% non-flammable. In fact, carbon dioxide is used in a lot of those Freon style fire extinguishers out there. And leaves very little residue. It is considered by most to be a green alternative, a environmentally friendly alternative to dry cleaning. Now, with carbon emissions standards and whatnot, the regulations that are trying to be passed to be more carbon neutral, obviously that does have some drawbacks to it, but it's still way better than the alternative. It's also a little bit more expensive, which is why you don't see as many carbon dioxide dry cleaners out there. So one little note that goes with this, and that is that if we are to do compression, if we're going to liquefy a gas, we have to be below the critical point. And that seems kind of obvious, right? Because if we are a supercritical fluid, again, we're not really truly a liquid. We're kind of a in-between phase. And so from a transport standpoint and whatnot, we're going to run into some problems. This is what a phase diagram looks like. Again, we can see that it's a graph. I'm going to move this out of the way. It's a graph. Along this line, here at 1 atmosphere, these are what we would consider our normal conditions for water. So water will freeze or melt at 0 Celsius. It'll boil or condense at 100. Those are things that we already knew about water. But what we can see also is that if we are at lower pressures, that boiling point comes down. That freezing point, ever so slightly, comes up a little bit. Up here, this is our critical point for water. You can see the critical point for water is not very easily attainable, 218 atmospheres of pressure. So that's, again, 218 times normal atmospheric pressure. And 374 Celsius, which isn't too difficult to reach, but you'd have some problems if you're going to try to use this material for doing things like washing or anything else. 374 Celsius is still very hot to exposed skin. Down here, the triple point, we can see that the triple point is just slightly above 0 degrees Celsius. And we're talking low pressures, 0.006 atmospheres. So that's 6/1000ths of atmospheric pressure. So to do an experiment where we actually see the triple point of water, what we would have to do is we'd have to use a vacuum jar of sorts. Just a closed container where we pump out almost all of the air inside of it and you leave just a little bit behind to give you that pressure value. All right, in terms of what could you be asked about a phase diagram, these are the kinds of questions I want you to be able to answer, things I want you to know. So, can you interpret this graph correctly? So, three questions here. What I want to know is, what is the state of matter for the water at these conditions? At 1 atmosphere of pressure and 105 degrees Celsius, what would we expect? Okay. Now, if you're unsure, what you can always do is draw yourself a little crosshairs here. I've got 1 atmosphere of pressure. I don't know exactly where 105 is, but I'm going to say it's just a little bit past the 100 mark. Where those two lines cross, that's where our phase is. So it's actually the yellow region here. The yellow region is water vapor. At 200 atmospheres and negative 15 Celsius, what are we looking at? So 200 atmospheres, let's estimate that's about here. Negative 15, let's estimate about there. We're crossing up in ice. 218 atmospheres of pressure, 374 degrees Celsius. That's the critical point. What are we seeing at the critical point? Say that again, Wyatt. Yes. Remember, critical point is the last place where we can see both of those phases and be able to tell them apart from each other. So what we would actually see there is we would see water in the liquid phase and water vapor in the gas phase together. And any of these points on these black lines, understand if we land on one of those spots, we're actually going to see both phases there at the same time. Think about when water boils. You're cooking a pot of spaghetti on the stove. You've got it on there, the water is boiling away. If you stuck a thermometer inside of that pot, what you would notice is that that water temperature doesn't change until basically all the water's gone. Phase changes are what we call isothermal, meaning they're at the same temperature, consistent temperature throughout. And if we allow them to occur, if we allow it to stay at that same temperature, what we will see is that they will interchange between each other. Now, when you boil a pot of water on the stove, you're continuing to add energy to that water, and that's going to drive the reaction to eventually convert everything into vapor. But if I was able to keep the water at the same temperature and close off the lid and turn off the heat source, what I would start to notice is that the water would continue to boil, but that domed surface would actually start to see condensation on top of it, as well as the water in the gas phase starts to turn back into the water at the liquid phase. And we'd end up seeing both happening at the same time. So when we're on one of these black lines, understand that both phases are there at the same time and they're both changing back and forth. The only way that we get from one to completely one or completely the other is if we add or take away energy, which means we change the temperature. Or I guess we could technically change the pressure too, but that's a lot harder to do in a reaction system. Okay, now closely related to this is the concept of a cryogenic liquid, a cryogen. By definition, a cryogenic liquid is one that is contained at less than negative 130 degrees Fahrenheit, which would be about negative 90. Using a phase diagram, the producers of cryogenic materials can liquefy the gas by either lowering the pressure, or sorry, increasing the pressure or lowering the temperature, or both. And if that final temperature, once we get it to that liquid phase, is less than negative 130 Fahrenheit, then we call the resulting compressed liquid a cryogenic material, or a cryogenic liquid. When it comes to cryogens, just like we saw with the phase diagrams, the terms critical point come into play here. So generally speaking, a cryogenic material is one that is going to have a relatively low critical point. So what we're talking about here usually are gases with low molecular weights, things like helium, neon, liquid nitrogen, liquid oxygen, those kinds of things, where we've got the substance itself at a relatively low temperature, and we need that relatively low temperature to get it to liquefy because it is so obviously a gas at pretty much every other condition. And so when it comes to cryogens, these two terms come into play. The critical temperature is that temperature where simply adding pressure isn't enough to liquefy the substance. And the critical pressure would be that pressure that is required to liquefy the gas at that critical temperature. Now you put those two together and you have what we would call on the phase diagram the critical point. I'll come back to this in a second if you're still copying. But if we think about that idea of the critical point here, using that definition, the critical pressure is the pressure where pressure alone is not going to be enough to liquefy. In this case, it's 218 atmospheres. I can see overall that for a lot of these, if I want to make water vapor into water, in a lot of cases, all I need to do is increase the pressure. But at 218 atmospheres, if I go beyond that, I can't do it. And that makes the critical temperature, the temperature at that critical point, 374 Celsius. So these two concepts, critical temperature, critical pressure, these are independent. These are of the same kind of quality that we described our critical point on the phase diagram. They're talking the same language. They are the same thing. Now, when it comes to hazards associated with cryogens, we have to understand that if and when a cryogenic vessel is open, what is going to first happen when that vessel is opened is that the gas that is trapped inside, or the liquid that is trapped inside, is going to rapidly vaporize and in some cases solidify other gases around it. Not a perfect example, but you can think of this. How many of you have ever worked with or seen experiments done with dry ice? All right, you take the dry ice out of the cooler, and what was the first thing that you notice? Go ahead. Yeah, yeah. Dry ice creates like this fog-like effect. And if you let it sit too long out on an open counter or something like that, you'll see that there are little bits of ice that'll form basically anywhere it can pick up water vapor. Now, that's not the dry ice that is steaming up. What that is as the dry ice is encountering the water vapor in the air, and there's almost always water vapor in the air, we call it humidity. As it encounters that water vapor, it is so cold relative to that vapor that it instantly condenses it. So now we have an airborne liquid that is still kind of in the gas phase. We know that better as a cloud. And clouds that are low to the ground are called fog. So that fogging effect that we see with dry ice is a result of that really, really cold dry ice pellet or puck or whatever it is that, slab, whatever it is that we use, interacting with the water vapor around it. Now that's dry ice, which is at a relatively, it's cold, but it's not super, super cold. Take that and compare it to something like liquid helium or liquid nitrogen, where now we're at temperatures under 30 Kelvin. Wicked cold. And you can see what it's going to do. You open up that container, it's going to do the same kind of fog machine effect. If you pour out that liquid, you ever seen any kinds of those flash freezing demonstrations on YouTube or in person, you know that liquid nitrogen can flash freeze pretty much anything in a matter of seconds, which is why you have to be really, really, really careful when you work with it. Make sure that you're wearing the appropriate PPE so that you don't get flash frostbite or worse. And so that's what we mean by this liquefaction and solidification business. It is so cold relative to the stuff around it that is either going to cause whatever molecules around it to either instantly liquefy if they're gas phase, or solidify if they are liquid phase, or sometimes even both. And what we tend to see often is this very thin layer of ice that forms around those kinds of objects because of the water vapor in the air. The other primary danger that is associated with them is because, and this really applies to any gas cylinder, but for cryogens, because they are held at such cold temperatures and their pressure is so low because of those cold temperatures, if they were in a situation where they rapidly were increasing in temperature, the pressures inside of the vessel can reach catastrophic levels very quickly, to the point where you could hit the regulated pressure for the container fast and have a potential explosion on your hands. Now, the general rule of thumb for a compressed gas is that, roughly speaking, about every 500-degree increase in temperature will cause a doubling effect of sorts. So here we have the pressure at about 1,000 psi at 70 degrees. 500 degrees later, that 1,000 psi is about 2,000 psi. 1,000 degrees later, it's about 3,000 psi. So the first 500 degrees caused it to double. The second 500 degrees caused the pressure to triple. And if we follow kind of the pattern out, the third 500 degrees would cause it to quadruple, which for most gas cylinders would mean that it's going to break. Most gas cylinders, with some exceptions, most of the ones that we see in our laboratories can stand up to about 3,500, 4,000 psi. Beyond that, it gets really sketchy. Now, when we talk about flammables in next chapter, we'll talk about what safety measures are put into those gas cylinders to help release the pressure more effectively and more safely. That's another discussion for another day. So, what impacts do cryogens have on other materials? Well, we already talked about this. Flash freezing is the biggest concern. When cryogens encounter material, they will flash freeze that material, which means any liquids that are inside of that material will instantly become solids. And the thing is, with instantaneous flash freezing, you end up getting very, very, very small, fine, solid particles. And because of that, they're very brittle, they're easy to break. The impact on your skin, basically you get thermal burns, frostbite. And depending upon the degree of exposure, they can resemble anywhere between first-degree thermal burns and third-degree thermal burns. And obviously, hypothermia is going to be a major consideration amongst those. And so that is it for our chapter 2 discussion here. All right, any questions about anything we talked about today or anything else from chapter 2? Here. Yes. Yeah, so for the, you've already taken the chapter 1 quiz, but for chapter 2 quiz, I would suggest having the conversion table somewhere nearby so that you can access it. But for the exam itself, I will give you an equation sheet of sorts that have those conversions on. Other questions? All right. Now, before I let you go,